Okay, so let's continue doing the kind of overview background material for this course and continue kind of trying to very efficiently and minimalistically get to where we want to get to start building models. So last time we ended up with, we talked about how, so string theory had a sort of idea of like a function that maps from a world sheet to a space-time. And we talked about how if we had a bosonic field, for example, you could write down an action for it, and that bosonic field. So last time, I think we could have something like x mu that mapped you from some world sheet sigma to some space-time n. And also we thought we could also have a fermionic field that maps you to n. And the first would have like we wrote down some action. You could write it down either as like a Navigato action or a Polyakov action. So last time I wrote like a Polyakov action, which has a kinetic term. So I wrote it for like massless bosonic fields, scalar fields. And we said that the kinetic part looks like the Klein-Gordon action essentially. And then if you do it for a spinor field, you get like, or a spin-half field, you get like a Dirac action. And then we said, when we wrote down these actions, we said there was a supersymmetry transformation between them. And the idea as well was that we had some kind of symmetries. So if we wrote down like a Poincare invariant action or some x mu and some sine mu, then we have some additional symmetries from Poincare, which relate to symmetries of the world sheet metric. So this metric sigma, so this world sheet sigma has some metric like h, a, b or something, which is a function of like sigma and tau. So the world sheet coordinates, and we said last time that there was some symmetries, diffeomorphisms, and Weyl symmetry. So the diffeomorphisms or diffeos essentially say that this world sheet metric transforms like a two tensor. So it transforms like that Jacobian, the two derivatives, the two coordinates, sigma and tau. So it's like a two tensor, HAB, and then the Weyl transformation is this phase factor, which is what we're going to talk about more now. So let me just check what we said last time. So let's say the Weyl symmetry would be like h going to like some exponential h of gamma. Let's say sigma tau h. Or whatever. And we said that this is the interesting feature. So the diffeomorphisms are basically like the diffeomorphisms aren't so interesting because they're essentially just standard like reparameterizations of the coordinates, symmetries relating to that. But the Weyl symmetries are interesting, and we wouldn't have predicted that it was going to be there at the start if we'd just sort of thought, well, we're going to write down a Poincare invariant action, blah, blah, blah. The fact that you got Weyl symmetry is the sort of novel part of string theory at this level. And this is takes us into the idea of string theory being a conformal field theory. So conformal field theory is just like could be a quantum field theory or string theory, which have this this property that the internal fields can be invariant under a changing scale. So this is like a scale factor in the theory, and yeah, and then now I'm going to kind of elaborate on what that symmetry means for us. So what I'll say without going into loads of detail is that you can kind of think of the problem like if we wanted to know like, oh, how do we sort of solve the string theory? Like how do we want to, so we want to know the states in the Hilbert space of the string theory. So the question of like solving the string theory can be kind of just thought about as a problem of essentially you would sort of solve, or let's say find the like irreducible representations, so the irreps of the conformal the conformal symmetry or conformal algebra. So we want to find the states that are sort of invariant under the conformal symmetry. And those will be the states. Once you look at the irreducible representations, those will be the states that are like our particles or well, our fields that are in the spectrum of the theory. So in order to make the conformal field theory structure more manifest, what we'll do is map sigma. So let's map sigma, the world sheet. So we'll map sigma such that like instead of using tau and sigma, we're going to use we're going to go to let's see, t. Sorry, we're going to map them with an exponential. This is called like a conformal map. And then we can just call that Z and Z bar. So we're kind of taking two real coordinates, complexifying them, and then taking the complex conjugates, the two coordinates, like mapping to a complex plane. And then if we have some fields, so for example, for example, you would write like a bosonic field, sort of as x mu, and then a function of z and z bar, or psi mu, function z and z bar. Okay. What else to say now? So obviously I'm sort of skipping out some details, but what we can think of, so these symmetries here, so diffeomorphisms and Weyl symmetries of this world sheet metric, we can think of these as like gauge, these are like the gauge symmetries. So the theory, you know, we shouldn't, the physics shouldn't depend on these things. So these are gauge. Okay. And that means that one thing you'll do in order to solve the theory is you want to sort of quantize the theory, go through the procedure of like finding the states of the theory in a way that doesn't depend on the gauge symmetries. So it doesn't depend on diffeomorphisms or Weyl symmetry. Okay. And so then that kind of like leads you down a few different routes towards, in particular, like quantizing the theory. But so one way you can do it is to sort of fix a gauge. at the start, and then look at the theory and try and quantize it. So you'd look at your fields, expand them in modes, and then take like, Dirac commutators or whatever of the modes, and then follow the sort of standard procedure in some sense. Or you could do something more rigorous, which would be like Faddeev Popov quantization, like BRST quantization. So BRST quantization is sort of like probably the most, I would say, the most rigorous way to quantize the theory, because it's essentially gauging variant. Okay. Whereas if you fix the gauge before, then the procedure to quantize the theory is a little bit less well defined, blah blah blah. But I'm not going to go through the full quantization of string theory. You can like look that up somewhere else. But what I'll say is that, let's say we're gonna generally work in the light cone gauge. That's sort of what the main point I want to make. So the light cone gauge. So let's say if we're in the light cone gauge, then mu from 0 to like d-1. So if our space-time is d-dimensional, then we can go to line cone coordinates where we just say, like, let's use I, and that's just from 1 to d-2. Okay. That's just a note for how we'll use that notation quite a lot. So I'll say a little bit more about the quantization approach, because I think it will be really useful. As I said, I won't do like the full quantization or anything, but just give you some kind of intuition for things that you might read in longer notes on the subject. So yeah, let's say we have a theory with x mu and psi mu. So the like d massless scalar fields and d massless fermionic fields. Then one thing I'll just notice that you've got the action, fundamental theorem of classical mechanics, as well as quantum theory is Noether's theorem, right? So remember that. So you've got your like action. Then Noether's theorem tells you if you have a symmetry, then it has some conserved charge. Right. And the most important sort of thing we'll pick out is the conserved, or the energy tensor, or the stress momentum tensor, stress energy tensor, whatever. So then this, if you took your action and checked your conserved currents, your sort of fundamental conserved current from like Poincare asymmetries, we've got this stress energy tensor, which is going to look something like this. I've written something like, so alpha prime is one of the things it's the constant, or the sort of parameter of string theory, that's the one parameter, unknown parameter in string theory that I probably left out the action last time, but I think it would be a 1 over here, and then we had the action like a Polyakov action, from Minkowski metric. We'd have something like this, similar to what you get in like a Klein-Gordon theory, this term, but with the scale related to alpha prime. And then there's going to be something like a fermionic part, which would have like, yeah, the kind of direct form like this, I guess. Maybe with a gamma matrix in there, or not, not sure, but yeah, probably. So I'm just looking at the Z part, so there'll be a similar Z bar bit. So if you have a function, so the functions of Z, I'm going to refer to as holomorphic functions in the Z bar anti-holomorphic. Then you have some. Then you'd have some super partner to that energy momentum tensor, which would be like delta x psi, delta x times psi. So that's G. G is it? That's a G. Cool. Super partner. So this is called like, yeah, the supercurrent. So super partner of T. And if we were to expand, so expand in modes. So this is like, you know, the procedure, you could write down your conserved currents. So this is like your conserved current related like Fourier symmetry essentially. And then this is what, you know, if you've got supersymmetry as well, you've got psi mu and x mu. So this current appears as the superpartner of T of Z associated to the supersymmetry transformation that we mentioned last time between x and psi. Then what you could do is quantize your theory essentially in terms of the modes of those currents. Instead of just in terms of fields, you could do it in terms of the currents, the modes of the currents. So instead of like expanding x and psi, we take like look at the currents relating to the symmetries. So if you expand T in modes, so the T, just writing very schematically, you could write the modes of T as Ln and the modes of G as, let's say, GR, sort of standard notation. And if you were to write down the like commutation relations according to like following the procedure of Dirac quantization, then these modes from these definitions will give rise to a super Virasoro algebra. So the super because you've got the supersymmetry between T and G, and the Virasoro algebra is just a certain type of kind of commutation relation with what's called a Weyl extension. So there's this extension. If you look at the commutators of Ln with Lm, then they form what's called a Virasoro algebra. But I won't. You'll see that in notes on the subject and in other places. But now let's talk a bit about quantization. Yeah, I'll rub that out. So then with the standard quantization approach, you know, you've got like a vacuum, you want to define some kind of vacuum state, and then you're going to build higher level states by acting with these operators, these modes. So you can think of you know, building like a big Hilbert space from and then you just have to classify the states according to irreducible representations of the conformal symmetry. And that's what we'd call like solving the theory at this level. So we have to find a vacuum. So if we want the Hilbert space, so to get like a Hilbert space H, let's say start with vacuums. Start with some vacuums. State. Some more chalk. Yeah, so you start with some vacuum, but so a key thing to note. So note that we've got a sign mu in our theory, so a fermion, and point with a fermion is that there are like essentially two choices in the vacuum. So like a spinor vacuum has two choices: spin up, spin down. So this is associated to like. So if you think about like so if we had like sine mu of z, so sine mu of z, we could act again with an exponential. So like so if we wrote like so sine mu of z with 2 pi I. I don't know why I'm writing like that. So let's say sine mu goes to e I pi of nu psi of z. Sorry, sine mu of z. Then mu equals 0 or 1, like periodic, which we'll also call like R boundary conditions or Ramond boundary conditions, or aperiodic, which we'll call NS as well. The theory is going to be invariant. Okay. So yeah, the NS is it's like also called Neveu-Schwarz aperiodic. So this is a sort of associated to the fact that the sign mu is going to belong in a Clifford algebra. It's going to give rise to a Clifford algebra. So you've got gammas. So you're going to have some gamma 0, which is like, not 2 eta something, right? And that's like doubly degenerate. The idea is, you can act on if you pick like one of these two choices and then act with the gamma zeros, then you can get the other one, and it's still part of the vacuum. So what you get is what we call a Ramond vacuum. So Ramond vacuum, which is like plus minus, spin up, spin down. Which we could also just write as R for both choices. So yeah, like I said, that what we could do is then we take the vacuum. So it could be either the vacuum for like, we also would have, the X naught, sorry, the X mu vacuum, 0. So some bosonic vacuum, and the spinor vacuum, you kind of like tensor them together, and then you act with the operators associated to the modes Ln and Gr, and then you build your Hilbert space from there. And that's sort of, so yeah, I'll just write that. So act with L, N, G, R, that there as operators to build states. And those states will sort of go higher and higher, like mass level or sort of conformal level. But we'll, yeah, so we'll think of that as like going up the mass levels. Right, and then should say something about, so there's an extra complication when you build this Hilbert space. So so important complication. To get the Hilbert space is that what we really want is the Hilbert space to have like we need to basically introduce a new projection. So some of the states we'll sort of project out, and I'll try and there's a few different ways to explain why you need this projection, but so let's say we have sort of some state phi in the Hilbert space. After, if we follow that procedure I just described, like acting with all the operators on those two vacuums, then we really want to take some what we call the GSO projection of these states. So let's just describe what this GSO projection does. So P GSO does the following. So one, it will like removes states with I think an odd number, an even number. So with even number of oscillators when we're thinking about the NS sector. So if we take the NS vacuum and then we act with fermionic oscillators, then it turns out that we don't want to take essentially if we have the ones with an even number and an odd number of fermionic oscillators, then the theory, so one thing we could say is it's not going to be modular invariant. So that's kind of going to be my main justification for this, but we'll kind of come to modular invariance a bit in a bit. We'll talk about it a bit more in a minute. But so I'll just tell you what this projection does to start off with. So remove states with an even number of oscillators from NS sector. So I mean by the NS sector, the state built from the NS vacuum. So the vacuum where the fermionic vacuum is an aperiodic fermion. And then it removes removes even number, removes states with even number of, this should say fermionic. Fermionic oscillators, even number of fermionic oscillators. From what is it, the spinor, from conjugate spinor from conjugate spinor and odd number for normal spinor. So just normal spinors. It removes even number from conjugate spinor reps and odd number from spinor reps. So it's just, again, it's choosing like half of the states for spinor vacuums with certain number of fermionic oscillators, choosing half of them, even or odd numbers of oscillators. And again, you can justify this. One way to justify it is model invariant. And so one kind of result of this, so the result of this projection is that it gives you an even, so this will give you equal number of degrees of freedom from NS and R sectors. And this would give you, having an equal number of degrees of freedom is related to having what would be like super multiplets. If you're going to have supersymmetries, you're going to have your states you're going to have the bosonic and the fermionic states, and they're matched up, and there's going to be equal number for every bosonic. There's going to be a fermionic state. So you want an equal number of degrees of freedom. If you don't implement the GSO projection, you wouldn't have a matching. You'd have twice as many. That's one way to sort of justify like retroactively looking at the results that it gives you. So yeah, and as we'll talk about, like usually, you know, string theory will start from a supersymmetric like starting point. So this is kind of a good thing in this context, right? There are like more rigorous ways to justify the GSO projection. One way to do it is if you don't have a GSO projection, I think this is the most rigorous way I've seen. So I mean, justifying with marginal invariance is solid. It's like a good thing to do, but I haven't explained what that is yet. But another thing you can say is if you don't implement this projection, then if you look at the Ramond vacuum, then so you've got these gamma. Trying to remember the details exactly, but there's essentially like if you looked at the conformal field theory, associated to the Ramond vacuum would be like an operator in the conformal field theory, like an operator that would give operator product expansions, and the Ramond sector would give you a branch cut. So you know when you like in the complex plane, like a log or something that cuts the complex plane. So there's yeah, from a more like fundamental conformal field theory perspective, if you look at that structure of the spinors in the Ramond sector, I'm trying to remember there's like an operator that gives you the Ramond sector from the NS sector. That's yeah, that would have a branch cut in it, which if you then did the operator product expansions, there'd be something kind of, yeah, this extra term that's like inconsistent with what you want. So that's kind of like one way to justify the GSO from more of a, if you want to like read more into it, but because I just wanted to say that because in a lot of places, the GSO projection does seem completely arbitrary, and like a lot of even like very good textbooks will just kind of just say, oh, we need to do this because it helps make the theory better. It doesn't explain the motivation behind it. Anyway, so that's the kind of like extra complication to formulating the Hilbert space. It's that GSO projection. Okay, so that's everything I kind of wanted to say about the quantization procedure, without actually doing any details. That's just like the philosophy, really. Now I'll give you the result of the quantization procedure, or one of the main results. right? So remember what we've got is a theory of x mu and psi, and we've defined those fields in terms of z and z bar. And then we derived these currents, we built an algebra, we acted with operators, we implemented GSO projection, we built the Hilbert space, we've got the states. And then we find that once we do that procedure, and probably the most rigorous way to do this, so as I said before, if we did this in the BRST quantization procedure, so the BRST quantization procedure introduces some ghosts into the theory, these Faddeev Popov ghosts, and they're the kind of costs you pay for keeping the thing gauge invariant. If you follow the theory through, you follow the quantization through, the only way that you can like cancel the there's sort of like an anomaly that would show up in the conformal theory if you aren't in d equals 10 is the dimension of the space-time. So you can also get this result from the other quantization procedures, but it's not as kind of like rigorous. But essentially, if let me see how I've written it here. So you could think of if you've got the fields on like the holomorphic and the anti-holomorphic signs, you essentially I don't know how to introduce this, but it's to do essentially with the ghosts that you get in the VRST theory have to kind of cancel. So this will give rise to, so a bosonic field, you can think of it as adding, like it has a charge under the conformal symmetry. And this charge is also called like the central charge or the conformal charge. So each component of the bosonic field is going to give you C equals 1. Okay, so you're essentially going to get like D of those. You've got mu running to D. And then each fermionic field is like C1/2. So you're going to get like D over 2. But then in like, let's say, yeah, the best way to do it is if you do BRST quantization, you'd have some ghosts, which are often called B and C, Faddeev Popov ghosts B and C, which are some fields which have like specific conformal charge. So these would be fermionic, I think, and then you'd have some other ones that are like associated to the sign mu. And overall, the conformal charge should cancel. So these will have like a negative charge, and then the whole thing should cancel to 0. Otherwise, you'd have like an anomaly. So the conformal symmetry would essentially be broken. So I feel like I'm going into more detail than I was planning to, but that's the kind of idea. And you can kind of see that this depends on D. And overall, if you write these, the conformal charge from these ghosts and the fields, the only cancels when D is 10. And that's probably the best way to justify why string theory has to be, for the symmetry to not be broken, essentially, the conformal symmetry to hold, which was, the theory gave you that symmetry, so you have to preserve it. Because that anomaly would, cause all sorts of repercussions and kind of ruin your whole theory. So this is probably the best way to justify D equals 10. So that's why the superstring. So the superstring being, a string with both bosons and fermions that have supersymmetry connecting them, is in 10 dimensions, and that's where we get it from. Right. So now, after that kind of schematic explanation, we're going to explain that, well, so one thing is, we could call this the type 2. So this would be like related to type 2 string. So type 2 string. You can also think of like, you have basically, because we defined the GSO projection before, where we had the even numbers and the odd numbers of states, there are essentially two ways to implement the GSO projection. So one, you get like half the states, one you get the other half, and then you kind of tensor them together from the holomorphic side and the anti-holomorphic side. And basically you get two choices. One's type A, one's type 2A, one's type 2B. And we're not going to be talking about type 2 string, but I just wanted to say that. So that's the kind of theory. So that in the type 2 string, you have these fields, and this mu would just run to 10, and that's your theory. And it's got supersymmetry in 10 dimensions. There are two choices. That's all I want to say about it at the moment. There will be a few lectures time in the past, but it's recorded in the future, but where we talk about type 2 string again, but mostly we're going to be talking about the heterotic string. So we can talk about that now. So let's talk about heterotic. Oops, that's completely wrong spelling. Heterotic string. Okay. The idea of the heterotic string is that, let's say this theory here, there's a supersymmetry on both sides, on Z and Z bar. So this theory has what we call, in space-time, we have n equals 2 supersymmetry in 10 dimensions. The idea in the heterotic string is, well, we could just put supersymmetry on one side. So let's say we have x mu Z and Z bar, but we only have psi mu Z. Then on the holomorphic side, we're going to have supersymmetry, but on the anti-holomorphic side, we're just going to have the bosonic, the massless scalars, or the bosonic fields. Okay, so this is the idea of this is that we want it to be n equals 1. But there's a cost of doing this, associated to what I said before about the derivation of d equals 10. So the derivation of d equals 10 in the BRST quantization, for example, for the ghost to cancel the conformal anomaly, we had to choose that d equals 10. But in this theory, the way you do the BRST is going to be a bit different, because there's no fermions, there's no fermionic space-time field on the anti-holomorphic side. There's only the bosonic ones. So you're going to have like different ghosts on the two sides. So cancelling the conformal anomaly becomes a bit different. And if you did the same thing as here, you'd get a conformal anomaly. Because on this side, there would be nothing to cancel out the C equals 10 from the bosons would not be cancelled out. So you need to do something to implement, like put extra fields on the anti-holomorphic side that are going to cancel out. We're going to be like, cancel out that conformal anomaly. Because so the idea would be like, so you could write, let's say we wrote it like this, so you'd have x mu of z and psi mu of z. On the holomorphic side, this would give you like, the theory would be d equals 10. and that will cancel out the charges. Like if you split up like the conformal charge to be C and C bar, then the C would cancel into D equals 10 on the left. On the right, so if I call it H and A, so holomorphic and anti-holomorphic, then the anti-holomorphic side, you'd only have x mu of z bar. It turns out, so on this side, the C bar, so the C bar would be cancelled, so C bar would equal 0. So on this side it equals 10, C equals 0, then if C bar is 0, this side would need D equals 26, which is the result that you get for the bosonic string. So if I never introduce this sign mu, then the fermionic contributions to the conformal charge would never have been there. And actually the bosonic string is the first string you usually learn about in string theory, has D equals 26. But here you've got an extra, so here you've essentially got like a mismatch between the two sides. On one side, the critical dimension of the string is D equals 10. On the other side, the critical dimension is D equals 26. But this doesn't make sense because, here, the mu is the same index. So it can't run on one side to 10 and one side to 26. So what we do is, we go, okay, well, we need 26. We essentially need 26 bosons, like massless scalars. So what if we wrote like x I of z bar? Okay, and then mu, we can still run it from like, 0 to 9, let's say. But then we can just run I from 1 to 16. So what we've got from this perspective is we've got some space-time fields with a mu on the anti-holomorphic side, which have 10, they fill out the 10-dimensional space. But then we have some fields with a different index, which is not a space-time index. It's like an internal index. It has nothing to do with the mapping to space-time. Okay, and this I is 16, so there are sort of 16 internal bosonic fields. That is the consequence of only having a fermionic field on one side of the string. But otherwise, we're happy because we've cancelled the conformal anomaly. We have a consistent string theory. So this internal I, typically like in like quantum field theory, if you have an index, like an internal index relating to an internal symmetry of the theory, it's like a gauge symmetry. Okay, so this would be like, this would give rise to like a gauge theory of some kind. Okay, and now I'm going to talk a little bit more about these extra fields. Okay, and what the further consequences are. And these are the key extra things about heterotic theory too. So it's going to be very important for us. Another thing we could say is, instead of having 16 extra bosonic fields, we could relate them to 32 fermionic fields, so real fermionic fields, like let's say lambda bar, A. So these would be real fermions. So A from 1 to 32 real fermions. And it's sort of this thing here is like fermionization, which is a way of basically writing in the conformal field theory. You can map the operator product expansions, which are like define your theory essentially in the conformal theory. Between bosons, you can essentially take the exponential of the bosons and then write that as a fermion, and you'll get the same operator product expansion. And that's sort of what fermionization, that's like part of what fermionization means. But the upshot of it is that a single boson can be replaced by 2 real fermions in a conformal field theory. You could then complexify the 32 fermions into 16 complex fermions if you want, just by like taking one, pairing it, plus, plus you could take, lambda bar 1 plus I lambda bar 2, or something like that, and then you get 16 complex fermions. Yes, as I said, these will generate like a gauge theory, or that so associated to them will be gauge currents. So if you have, for example, the fermions, you could write like lambda A, lambda B star or something. That would be like a fermionic current associated to a U1. This would be like a U1 current. And you could build a kind of gauge theory. And there's going to be 16, with like 16 of these type of things. So let's say these are complex. So how about now I say A runs to 16, and these are complex fermions. Then something like this gives rise to the U1 current. And then there's going to be 16 of them. So we could imagine we're going to get like a rank 16 gauge group. Makes not rigorously explained, but so what we're going to find is we're going to talk about modular invariance next in this theory, and we're actually going to find that modular invariance is a symmetry of this theory that's going to constrain what gauge group we get. So so modular invariance we'll talk about now. Will constrain this gauge group. And we'll find that we only really get essentially 2 choices where we keep n equals 1 supersymmetry. These groups will have rank 16. So shall I continue now, or is that enough for today? Do you want me to talk about modular invariance a bit?
Yeah, you can go first.
I'm trying to remember where the first lecture actually started.
No idea.
Can you get the first lecture off on your thing?
Yeah, that's true.
Because it might be that I actually did this. I kind of feel like I might have done in the first. Yeah, I think I did. I think this might actually be where I get to.
Lecture 1.
The introduction to
Lecture 1, 3 theoretics.
Yeah. Yeah, maybe we're very close. We're very close. I'll do like 5 minutes. Oh, because it looks like I don't explain why we're interested in the torus. I'll try and do now. Okay, right. So just say something about modular variance quickly. And
Do you want to do video like all that stadium?
I don't know. I could try and edit it, I guess. I've never edited one before. But... Yeah. Okay. So modular variance. As I said before, modular variance is the most important thing about string theory. I guess how we can introduce the next very important idea that's getting us very close towards kind of really starting like model building is is if we think about like perturbation theory in string theory for strings. So I did say last time about how heterotic strings that we're looking at are always closed. So we only worry in this course about closed strings. And that's we talked about last time how you can have a string theory with only closed strings, but you can't have a theory of only open strings, because open strings can always join together to make closed strings. But okay, so if you've got closed strings, perturbation theory, the amplitudes, they sort of will look like, you get something like this, which is like a tree level. So tree level amplitude. This is giving rise to a genus 0 surface. So this is the world sheet. We're looking at the world sheet. So this is a world sheet where basically nothing happens. Okay, or this, it's just a surface with no holes in it. So that's the tree level. Then if we wanted to go to the next level, so I'm kind of using the fact that in string theory, you're creating, because you're in high dimension, you've got a 2-dimensional surface, and then the strings come in, they create shape, surfaces like shapes, topologies, and the way you classify topologies in maths is always with the genus, the holes in the surface. So sometimes you have to, in other parts of string theory, you have to look at things like the other topological properties of the surface. But the way to classify these tree level amplitudes is just with the genus of the surface. So this would be, say, a genus 1. So G equals 0, G equals 1. This is the 1 loop. And genus 1 surface is a torus. Okay. And then you can go to 2 loops. Okay. So you think like a 1 loop, well, what would that be? Is like if you had a string and then it looped around into itself. Okay. So this would be G equals 2. 2 loop. And then you could keep going higher and higher. This is just like the analog to Feynman diagrams. what we'll talk about is that associated to each one of these amplitudes is a partition function, which essentially describes all the important information about the theory on each particular surface, on each particular amplitude topology. So the first one, we have some object that we're going to define, partition function z, and at 0, we z0, let's say. Then at one loop, you're going to have something like z1, which would be like the one loop partition function, which is going to give you all the information about the states that can propagate on this surface. And then you have like the z2, etc. And what we're going to find is that the theory at this level, so the tree level heterotic amplitude, is it's sort of uninteresting, trivial, doesn't give you any constraints on the theory. Nothing happens. Essentially, more or less. We can talk about more about that and more about these amplitudes maybe in a later lecture, but this this amplitude is going to be the next simplest amplitude. It's going to turn out that all of the interesting constraints, apart from a couple of very small details, come from this loop, this one loop amplitude. So this is like all interesting constraints. Yeah. So we're going to be looking at the torus amplitude and formulating the theory on the torus. And we're going to get all of our constraints, which is going to be based on modular variance from the one loop theory. Okay. And the reason that the higher loops don't really matter is because just from a mathematical topology point of view, is if you want to create like a higher and higher genus surface, it's really can be done by just taking the one loop. So once you've got one genus, you can just sort of you can do this thing like you have a higher genus surface, you can do a decomposition into just like a product of genus one surfaces. So any higher loop, like n loop object, can be called like a modular decomposition into sort of like a product of the torus, load of toruses. So that's kind of why we're going to be interested in this one loop amplitude. Yeah, so the world sheet, we're going to say, okay, well, what happens? World sheet's a torus. What states can be built on that torus? And yeah, we're going to say that the partition function at one loop is going to be like a key part of our results. The partition function at one loop will contain all the information about like the Hilbert space. For example, it'll be like the sort of object that like defines our theory. Okay, so I think that's probably where we got to the right place to stop. And we've done about an hour, so is there anything else I should say? Yeah, I think I cover the rest next time. The modular variance will be essentially the symmetries of the torus. So if you have a parameter on the torus like tau that defines a point on the torus, we essentially have two components to it. And there's a mapping that's just, there's like basically two symmetry operations where you relabel the tau, and it shouldn't change the theory because it's just a relabeling. And those symmetries that define the relabelings are the modular group, which gives you like the modular variance. And then the partition function is going to be an object that carries, that contains all the states in the theory, but written in a modular invariant way. Okay, so I think that's a good place to stop. Any questions? Maybe we should do like a Q&A lecture another time. Stop.